Okay, so in this video, what we're going to talk about is doing some naming of ionic compounds. Hopefully you remember some of this from last year, and this will all be review. So the first thing, naming positive ions, right? You remember those are cation ions. And this one, as it says, is easy. When naming a positive ion, the element just keeps its name and the word ion is added after it, right? So in the case of sodium, Na, when it becomes an ion, right, losing an electron, sodium atom becomes sodium ion. Pretty easy. Negative ions, right? This one, pretty easy too. So when you're naming a negative ion, the element's ending gets dropped and the suffix "ide" is added in its place. The word ion is placed after that. So as you can see, F, fluorine, right? No charge, it is a fluorine atom. When it gains an electron, becoming a negative ion, right? An anion, it becomes a fluoride ion. So then putting those two together into an ionic compound, right? Simple ionic compound in this case because it is composed of a metal cation and a non-metal anion. And to name the compound, right, it's really easy. The names of the ions are just combined without the word ion, right? So a sodium ion combining with a chloride ion, right? Positive, negative, sodium metal, chloride non-metal. They become sodium chloride, right? Easy enough. Same with writing the formulas for simple ionic compounds. You're just going to kind of smush together the two symbols for the elements that go into making up that compound. So the one thing here, like it says, when writing formulas, you must also consider the charges of each ion and steps that must be taken to balance the amount of positive and negative charge so that the overall charge of the compound is neutral, right? Hopefully you remember, you do this by adding one or more of both ions to the formula and indicating the number of ions present with subscript numbers. So looking back at the periodic table, hopefully we all remember that we have some common charges here, right? Group 1, all plus 1, group 2, all plus 2, group 3, plus 3. Here, group 4, right, or column 14, plus or minus 4, depending on the situation. Here, minus 3, minus 2, minus 1. All right, so those are the common charges for everything on the periodic table. We will talk about everything in here, right, the D block, in a moment. Hopefully, though, you remember that. And also keeping in mind that our metals, right, are basically, all this stuff in here, right? And our non-metals are this section over here, right? So metals and non-metals. Gotta love that great handwriting. Okay, so some simple ionic examples. All right, we saw one, it was sodium chloride. Another might be lithium fluoride. All right, lithium, we know it's Li, fluoride, fluorine. If we look, this has a plus 1, this has a plus 1. So when we go to write the formula, right? Both of these cancel each other out, plus 1. Oops, sorry. This is actually minus 1. My mistake. So when we go to write these, right, they both balance out. We don't need any subscripts, so this is just LIF. However, if we look at something like, let's say, sodium oxide, right, that's going to be sodium, Na, oxide, O. If we look on the periodic table, sodium plus 1, oxygen minus 2. All right, so here we have plus 1, minus 2. They're not balanced, so we have to balance this out. So the easy way is to take the subscript from the opposite element and use it as a subscript for the other, right? So in this case, we would have Na2O. Now, you could put the 1 down here, but you'll never see that. Well, almost never. Because the fact that you've written the O here, right, tells me that you have at least one of them. So another example might be something like aluminum sulfide. All right, we know aluminum, Al, sulfide is S. So aluminum, if we look on the periodic table, plus 3, sulfide minus 2. Right, and so now we can use our trick. Just cross the numbers. Easy enough. Al2, S3, right? And that makes our charges balance, right? Because if we have 2 things that are plus 3, that's plus 6. And if we have 3 things that are negative 2, negative 6. Right? So it all balances out. So now, moving on to D block. All right, I said we would talk about it. Hopefully you remember this, that the D block, there are no common charges for the elements. All right, they each have more than one charge that they can have. And so in this case, right, we're going to need to put a Roman numeral in the name to indicate the charge, and you can figure out this charge based on what it is paired with in the compound. So to try some examples of this, all right, we will go with, let's say, iron oxide. All right, we know Fe, iron, oxygen, oxide. Right, and I left a little space here for our Roman numeral. So if we look on the periodic table, right, we know that oxide has a common charge, minus 2. Right, there's 3 of them. And so we know that the total charges from those is minus 6. Because we've got a minus charge, or a total negative charge of 6, we need this to be the same. All right, we need as much positive charge as there is negative. But now instead of multiplying, right, we're going to say 6 divided by 2. So now we know that each iron has a charge of positive 3. So we call this iron 3 oxide. That's it. That's how you do it. That's all there is to it. All right, going the other way, we could do something like chromium 7 phosphide. All right, so chromium, Cr, phosphide, P. So we know this has +7. If we look on the periodic table, -3. And we can cross the numbers. So we end up with Cr3, P7. So the only thing you want to watch here, and this goes for all your formulas, is if you can reduce these numbers, you need to do that. They need to be in their lowest numbered form if you can reduce them. Here, we can't reduce this. 7 is not divisible by 3 evenly, and you can't have fractional or decimal subscripts, so that is fine. Okay, polyatomic ions. So polyatomic ions, they contain more than one atom, but still have a charge, right? Easy ways you can identify them. In a formula, they will always have more than one element in them. So if your ionic compound has more than 2 elements present, it definitely contains a polyatomic ion. Polyatomic ions usually have 2 or more non-metals bonded together. So if your ionic compound contains more than one non-metal, it has a polyatomic ion. And if more than one polyatomic ion is needed to balance the charge of the compound, it will be in parentheses with the subscript outside. Hopefully you remember all these rules. And here we go, 1 or 2 polyatomic ion examples. Oh, by the way, because you're in AP now, you will have to memorize the common polyatomic ions and their charges. So enjoy. Let's start out with one of the only positive polyatomic ions that you will need to know. Ammonium. And we'll go with ammonium sulfide. So ammonium, we can look it up on the table, or if you have it memorized, you know that it is NH4. And sulfide, we saw that in an earlier example, S. So ammonium, charge +1, sulfide -2. We do the same thing here, right? The trick still works. And here, right, we have NH4. Now remember those parentheses, because you don't want to tell me that there's 42 H's in ammonium. You want to tell me that you have 2 ammoniums. All right, so we have NH4, 2S. And that would be ammonium sulfide. Another common one that you might need to know, right, is carbonate. So we can say calcium carbonate. And so calcium, we know Ca, carbonate, CO3. If we look on the periodic table, calcium +2, carbonate -2. So here, right, they're already balanced. So we just say Ca, CO3. Great. As easy as that. This is the last one in this video, I promise, probably. Hydrates. So, many ionic compounds contain water trapped in their crystal lattice. So, it's shown in their formula, usually as a specific known number of water molecules present in the lattice. In formulas, the water is placed at the end, separate from the others. And a number is placed before the H2O to indicate how many molecules are present. And in naming, the compound is named normally, as you would any other compound. And then the word hydrate is added at the end with those lovely numerical prefixes to indicate how many waters are present. So let's do an example going from formula to name and then name to formula. So one that you will come across most often, or that I come across most often as a chemistry teacher, is copper 2 sulfate pentahydrate. We have a large bottle of this in the chem supply room. It's a very nice blue color. It is also quite toxic, so don't drink a copper sulfate solution. So if we're looking, we'll do this formula. Copper, we know is Cu. Sulfate, you will memorize it, SO4. So we know the copper's charge is +2 because it says it in the name. And sulfate, we know because we've memorized it, its charge is -2. All right, so these are already balanced out. Great. We know that copper is 2 sulfate, C2, Cu, SO4, and then we put in the hydrate. So pentahydrate, penta being 5, hydrate being water, H2O, right? So you can remember anytime you see hydrate, it's water, because what do you drink when you want to hydrate? You drink water. It's good for hydration. Okay, going from formula to name now. Let's see. Let's do magnesium bromide. And we'll add some waters in here. Okay. So, I just told you what this is, right? This is a simple ionic compound, magnesium bromide. Magnesium bromide. And then we've got these waters over here. In fact, we've got 7 of them. So when we look at the prefix for 7, sept. So we have septahydrate. Just like that. That is how we do it. Okay, so to wrap this up, the big takeaways, things to remember: ionic compounds are made from a metal cation and a non-metal anion. The cation is always the first element in the name and formula. The charges of any ions present must be balanced so that the overall charge of the compound is 0. Any metal in the D block, right, transition metals, need a Roman numeral in the name. The Roman numeral indicates the charge. Polyatomic ions can be identified by looking for either more than 2 elements in an ionic compound or 2 or more non-metals in an ionic compound. Okay, thanks.